Alice has a delicate quantum particle that she needs to deliver to Bob. A classical bit stays fixed at 0 or 1. This qubit instead occupies a superposition, representing a specific unstable probability of being both. If we map this state on a sphere, we see a specific mathematical identity defined by the variables alpha and beta. This precise coordinate is what Alice needs to transmit. But physics presents a roadblock. The no-cloning theorem states that we cannot create an identical copy of an unknown quantum state. Alice cannot duplicate the particle, and if she tries to move the physical carrier, the journey will likely cause decoherence, bumping into the environment and destroying the state. She must find a way to transmit the information without moving the physical particle itself. To bypass this, she relies on a quantum resource called entanglement. Albert Einstein famously questioned the validity of this phenomenon, calling it spooky action at a distance. Entanglement links two separate particles so that their properties are shared. Measuring one instantly dictates the state of the other, regardless of the distance between them. Alice and Bob can use this correlated bridge to transfer the mathematical identity of her qubit across space. This setup creates the channel. By firing a laser into a specialized crystal, we generate a brand new pair of entangled photons. These photons are in a Bell state. Their fates are perfectly linked in a shared superposition. The pair is then separated. Alice keeps her photon, while Bob takes his half to a distant location. Alice now holds two particles, her original fragile qubit and her half of the entangled bridge. Bob sits miles away with the final piece of the connection. To begin the transfer, Alice forces her original qubit and her entangled bridge particle to interact. She performs a Bell state measurement, colliding the two into a single joint entangled state. This measurement has a destructive cost. Alice's original qubit is lost. The probability wave collapses, leaving her with two classical bits, a 1 and a 0. Because of the shared entangled bridge, the exact moment Alice measures her particles, Bob's distant qubit instantly transforms. Bob's qubit now mirrors the mathematical information of Alice's original particle, but the state is currently scrambled and unreadable. Alice has successfully pushed the information across the universe, but Bob needs one final set of instructions to resolve the data. Those instructions are the two classical bits Alice just generated. She sends them to Bob through a standard, slower-than-light channel, such as a radio signal or a phone call. Because Bob must wait for this classical message to arrive, the protocol cannot transfer information faster than the speed of light. When Bob receives the bits, he performs a specific mathematical operation, a unitary transformation, to rotate his scrambled qubit. This rotation shifts the probabilities back into their original configuration, perfectly reconstituting the state Alice started with. This process was first verified in a lab by researchers like Anton Zeilinger, using photons to prove that quantum states could be reliably moved. The physical matter Alice started with never actually moved to Bob's location. Instead, the protocol disassembles the identity of a particle on one side and ensures that identical identity is rebuilt elsewhere. By separating a particle's identity from its physical matter, quantum teleportation demonstrates that information can be treated as a transferable resource, independent of the atoms that carry it.